Yeah. See, yesterday we had a basic definition of congruent. You consider three numbers A, B, M with the condition A comma B should be greater than 0 and also M. M is positive integer. We have two possible cases. Consider A minus B if M does not divides A minus B and M divides A minus B. If M does not divides A minus B, then we say A minus B cannot be expressed as K times M. This implies A is not congruent to B mod M. So in this case, we have A minus B can be expressed as K times M. That implies A is congruent to B mod M. So understand both the way. When M divides A minus B, we can write A congruent to B modulo M. When A is congruent to B modulo M, we can say M divides A minus B. See, what do you mean by A congruent to B mod M? By division algorithm, we can say M is divisor and A dividend and B is remainder. That means we can say if A is congruent to B modulo M, we can express ABM in using the relation that is capital small a equal to it is M times Q plus B. This is basic division algorithm. See, ultimately my number theory works only on division algorithm. Yesterday we had division algorithm. We had been to GCD, using division algorithm, how to find the GCD, everything we covered. So ultimately rule making is GCD. For that we want division algorithm. Using division algorithm we went one step ahead called Euclidean algorithm. So try to understand in a very logical way what is congruent. If I say congruent, what it do? So A is congruent to B modulo M. Then M divides A minus B. If M divides A minus B, then using division algorithm, I can write A equal to M into Q plus B, where A is a dividend, M is divisor, Q is quotient, B is going to be the remainder. You know the condition of remainder. Remainder should be always, that is 0 less than magnitude of B and should be less than M. It can be equal to 0. But never equal to M. So it should be lesser than the divisor and it should be between 0 and the divisor, excluding divisor. Now what are the properties? You have many properties on division or what you call the congruent component, and very majorly applying components are going to be A is congruent to B mod N. C is congruent to D mod N. So then immediately we can write A plus or minus C is congruent to B plus or minus D, so mod N. And one more property, this is all basic property, AC is always congruent to BC mod N. AC congruent to BD mod N. That is, I can multiply A with C, then multiply B with D, and I'm going to get the modulo class N. The one more property I can call here, with respect to one modular class, if K not equal to 0 belongs to integer, then A times K is always congruent to B times K mod N. And one more property, the GCD of, if the GCD of A comma B equal to say M, then I can write here, then A divides M is congruent to B divides M mod, already I use, mod N divided by M. This is a fundamental property and most important property I would like to go now. It is called reflexive property. A is always congruent to A mod M. A congruent to B mod M implies B is congruent to A mod M. And one more property, A congruent to B mod M, comma, B is congruent to C mod M. Necessarily, A should be congruent to C mod, a fundamental property. And most important property that we will be carrying for the application part, that is using linear congruent, Diophantine equation and Chinese remainder theorem, are going to be this one and one more called exponential rule property. A congruent to B mod M. If this happens, immediately we can write A raised to N is always congruent to B raised to N mod M. And you can use, if you use here N as a modular function, then you can call as K here, where K is positive integer. This is called exponential rule. Very, very important, and this is also very important, and remaining may not be that important, but generally we are be calling all these property and should be recorded. And two most important properties are, when you have two congruency, I can multiply to get the congruency over the same congruent value. Another one is, when there is a congruency, I can raise the power of the dividend as well as the remainder by a non-negative positive integral value. It is basically called exponential rule. And if you take care of this and if you take care of these, 100% most of the application part you can enjoy. Particularly I can say linear congruent and Diophantine equation and Chinese remainder theorem, which is in term I can go one step ahead, cryptography, that is coding and decoding. Now we will go with, I will like to move towards these three components, linear congruent, Diophantine equation and Chinese remainder theorem, using all these property what we discussed. Now we have linear congruent. From here you should be cautious and careful and try to recall whenever what are the information which has been called for you in the previous classes, you need to call back. What is linear congruent? A comma B n be any positive integer. Generally, yesterday I told you it happens for even negative, but most likely we are dealing with positive integer, and the same way I can deal with negative integer also. Generally we are going to do only with the positive integer. Then Ax congruent to B mod n is called linear congruent, with unknown x. So this linear congruent this linear congruent has two possible cases. One is we get solution in X. Second one, we may not get solution in X. That is basically we call no solution. Now I will discuss no solution case. There is only one particular case. Then I go with possible existence of solution in the case of linear. Consider the GCD of A comma B, which are the given two number. Say the GCD is M. If M does not divide N, then it has no solution. It has no solution. If M divides N, then it has M incongruent solution. And very typical case, if M is equal to 1, that is GCD of A comma B equal to 1, that is a relatively prime, then it has unique solution. So this is a linear congruent expression. The first property or first typical case we are going to come across number theory, or I can say the fundamental component required for the application part. Ax congruent to B modulo n, where x is an unknown value, and you may require to find the value of x satisfying this particular expression. But again, you may get an x satisfying this expression, or you may not get. That is, it may have a solution, it may not have a solution. When you say it don't have solution, it all depends on the GCD. That's why yesterday I told you, in the last class I told you, GCD is a rule making and it is a superior when you go with the number theory and related applications. Get the GCD of A comma B, say it is going to be M. If M does not divide N, modulo class, if M does not divide N, then it has no solution. If M divides N, then it has M incongruent solution. I will show you how exactly incongruent solution we can find. And M equal to 1, that is GCD of A comma B equal to 1, that is relatively prime, then it has unique solution. I'll take one or two simple example. I'll show you whether solution exists or not, and if it is exists, how many solution it exists, and if it is a unique solution, under what case it has a unique solution. I'll go with an example. You consider 3x congruent to 6 mod 5. Carefully observe. You compare the standard form with my particular case. So Ax congruent to B modulo n. When you compare Ax congruent B modulo n, when compared 3x congruent to 6 modulo m, obviously I can write A equal to 3, B equal to 6 and n equal to 5. And what is the GCD? GCD of A comma B, that is GCD of 3 comma 6. Generally we write G. Yesterday I told you why I always use the word G, because starting component, starting letter of the GCD is going to be G. Generally we use that. My symbol and my definition should match in that way. Some author uses D and generally I use G. The GCD of 3 comma 6, yesterday I told you how exactly we can find GCD. There are two approaches. One is classical approach, another is Euclidean algorithm. Classical approach is the numbers are simple, and Euclidean algorithm the number of too large. It's a simple, generally I can say directly 3. The GCD between 3 comma 6, GCD of A comma B equal to 3. The next question is 3, that is I can say 3 does not divide 5. That is G does not divide N. See the case number. I am calling M as GCD. Here I am calling G as GCD. And I have called N, your N equal to 5. 3 never divides 5. That is G is not dividing N. The GCD of the given pair is not dividing my divisor. That is N. That is called modular value. Immediately I can say no solution. If you have any such linear congruent under the condition, no funny in going with the solution because it has no solution. I'll take one more example where I can find many solutions. I'll show you now. You consider 4x congruent to 12 mod 8. So you can write your own problem. So mathematics, that's a beauty. Once you have a good control, you can write your own problem, you can solve your own problem. That is the right way. You consider A equal to 4, you consider B equal to 2, given we have N equal to A. Let's see. Get the GCD of 4 comma 12. Again, it's a very classical way of finding GCD. Yesterday in the last class, I already discussed how to find the GCD. I can write here directly 4, which is going to be G. Here I used M, I am using G here. Next question is, do my 4 divides 8? Yes, 4 always divides 8. This implies my GCD of the given pair of number A comma B divides N. This implies it has, see here, if M divides N, it has M incongruent solution. It has, what is G value? G value 4. It has 4 incongruent. It is very important. Incongruent. It's not congruent. Incongruent. That is the other way solution. Later we are going to discuss how to find the solution, all these 4 incongruent solutions. First you should understand what is linear equation, what exactly you are supposed to find, when you can find, under what condition you can find, under what condition you cannot find. So all those cases I am just giving a critical or a bird view. I will go with example number 1. See, I have 3 possible cases. One is no solution. Already I took a case. Second one is have M incongruent solution. I took a case. Now I should go with a case where it has unique solution. I will take case study. 3x congruent to 7 mod 5. Or I can say here, I can write 11. 3x congruent to 7 modulo 11. What is A value? 3. What is B value? 7. What is N value? 11. I am just comparing my original standard linear congruent equation. I am just comparing. I got the 3 value. Now what is GCD of 3 comma 7? That is GCD of A comma B. That is GCD of 3 comma 7. It is going to be 1. Again, yes, in the last class I explained how to find the GCD. Again, there are 2 approaches. One is classical approaches. GCD, greatest common divisor, get all the divisor, get the common, get the biggest one. That is a classical approach. It works only when the numbers are too simple. When the number is too large, the better we apply division algorithm. Using division algorithm, we move towards Euclidean algorithm. Using Euclidean algorithm, I can find GCD in a more easier way rather than the classical approach. Always I advise you practice, learn division algorithm, Euclid algorithm to find the GCD. Maybe simple or complicated, better learn that. Now GCD equal to 1. I can write this is G. See what the condition says. If the GCD is 1, if they are relatively prime, then it has unique solution. It has unique solution. So these are the three possible cases when you go with your. The question is, no solution, nobody will cry. Unique solution, nothing to worry. The question is, I want one or two problems to be discussed when you have more than one solution and all those solutions are going to be incongruent solution. I'll take one or two simple examples, I'll go with that. Okay? Solve the linear congruent. Solve the linear congruent equation 9x congruent to 6 mod 15. See, before dealing with this, you can highlight how we can find the incongruent many solution. So I'll be highlighting here. So you consider standard form Ax congruent to B modulo n. GCD of A comma B, that is equal to G, not equal to 1. If it is equal to 1, only one solution. If it is not equal to 1, I may get many solutions. Now you consider whether G divides n. Yes, when G divides n and G divides n, then we have G incongruent, G number of solutions. So incongruent solution. Now how to get those incongruent solution? To get those incongruent solution, the general representation is x is equal to x naught plus the n divided by g times t. You know what is x naught? Primitive solution. It is called primitive solution, fundamental solution, primitive value. And you know what is G? It is GCD. And what is N? The divisor. That is called modulo value. And T, it is an integral value. It has to run from 0 to G minus 1. Take care. 0 to G. This is the general representation of finding many solution. When the GCD equal to G not equal to 1, G divides N, then G has G incongruent solution. How to find the G incongruent solution? I can go with this. Now the question is, you know N, you know G, you know how to run the T value 0 to G minus 1. Only your ambiguity or your doubtful case is how to get the X naught. I'll go with this problem. Carefully see now. What is A? 9. What is B? 6. What is N? It is going to be 15. What is GCD of A comma B? That is GCD of 9 comma 6. That is equal to G. Again, simple. Already I came with the ready solution, and you need to practice. You should learn how to find the GCD. It is going to be 3. The GCD between 9 comma 6 is equal to G equal to 3. The next question is, using that 3 or using that G, I want to know whether there is a solution, and if that is the case, how many solutions. Consider G division N. That implies 3 divides 15. Yes, 3 always divides 15. So it has more number of solutions. That means it has 3 incongruent solution. How to find 3 incongruent solution? I can write x is equal to x naught plus the n divided by the g times t, where t goes from 0 to g minus 1, where g is a GCD. That is, x is equal to x naught plus n. What is n value? 15. What is g? 3 times t. So on simplification, we can write x is equal to x naught plus phi t, where t running from where t equal to 0 to g minus 1. What is g value? G value is 3. 3 minus 1, it becomes. So take t equal to 0, take t equal to 1, take t equal to 2 and just substitute here. I am going to get 3 incongruent solution. The only hidden component is to get the x naught. How to get the x naught? We go back to the original problem here. I will use the property of congruent. I will make the expression as simple as possible. See here, we can write gx, it is going to be 9x here. 9x is congruent to 6 mod 15. We can write this as 3 times 2x, 3 times 3x, pardon, equal to 3 times 2 mod, we can write 3 times 5. Use the property of congruent. If there is a GCD common throughout, I can remove that GCD. So divide by 3, then we have 3x congruent to 2 modulo 5. Now once you find the x naught, x using this, that is your x naught, substitute, I am going to get. Now how to find the value? See, there are two approaches. One is by inspection. Another is modeling. I can say modeling. There are two approaches. One is called inspection method, another is modeling. I am going to teach you both the method using the same example. What is inspection method? Assign different values of x. Again, have the clarity. I told you A is congruent to B mod n. This is dividend. This is a dividend number you want to divide. This is a divisor. This is a divisor, and this is going to be quotient. Ultimately division algorithm, nothing else. My number theory runs only on division algorithm and parallelly composite prime number, and the rule maker is prime number. Now what should be the condition on B? B should be always less than n, it can be 0. Now what I am going to do here, I will assign x is equal to 1. I will check whether 3 is congruent to 2 modulo 5. Again, I will do here. A congruent to B modulo n implies n divides A minus B. N divides A minus B. Left minus right, that value is divisible by that modular operator n. What is 3 minus 2? Left minus right, 3 minus 2, 1. So definitely 5 never divides 1. That means x is equal to 1 is not a solution. By inspection, go to the next value. Take x is equal to 2. Then we have 6 congruent to 2 mod 5. Again the condition is take the left minus right. Left minus right is 4, and 4 cannot be divisible by 5. So 5 never divides 4. X is equal to 2 cannot be a solution. This is called inspection method. And this inspection method is valid and is applicable whenever the modulo operator is small. When the modulo operator is big, either go by modeling or by Euclidean algorithm. I will show you with one example of Euclidean algorithm. Now you take x is equal to 3. Let us see what will happen. 3 into 3, this is where I am using. 3 into 3, it is going to be 9, congruent to 2 modulo 5. Take the difference. 9 minus 7, 9 minus 2, 7. 5 never divides 7. Never divides 7. So x is equal to 3, again cannot be the solution. Go for x is equal to 4. Then we have 4 into 3. What is 4 into 3? 12 is congruent to 2 mod 5. What is 12 minus 2? 10. Definitely 5 divides 10. Therefore, x is equal to 4 is a solution. This is not a solution. This is not a solution. This is not a solution. But this is going to be a solution. See that value by inspection you got, it can be taken as x naught. So here I will take x naught equal to 4. Once you got the x naught equal to 4, you can come back and substitute here, run the value t from 0, 1, 2, I am going to get 3 values. So, no place for me. Shall I erase this part? I will erase this part. So, I can show here, this implies, I want 3 incongruent solution. 3 incongruent solution. How to find the 3 incongruent solution? This is the formula. I can write x is equal, what is x naught? It is 4 plus 5 into t, where t has to take from 0 to 2. That means take x is equal, take t equal to 0, one solution is x is equal to 4. Take t equal to 1, another solution is x is equal to 9. Take t equal to 2, another solution is x is equal to 14. These are the 3 solutions for the given linear congruent equation. Why I got 3 solutions? Because the GCD is 3 and 3 divides my divisor. GCD is 3 and 3 divides my divisor, and according to my standard representation, your incongruent solution can be obtained using x is equal to x naught plus n by g times t, where t running from 0 to g minus 1. So 0 to 2, we have 3 incongruent. This is one approach, that is basically we call try and error. Do inspection. Take x is equal to 1. So my equation is not satisfied. What is the equation? Equation, ultimately this is my model. N divides a minus b. 5 never divides 1. 5 never divides 4. 5 never divides 7. But 5 divides 10. Therefore, these are the 3 cases where I should not consider. The only case I can go with x is equal to 4. Now you like to enjoy the same approach using model. So before explaining the modeling method, yesterday, that is the previous session, I explained how I can convert the given modulo class into an expression. So directly I will go with that, recall it now. So we can write 3x is equal to 5 times k plus 2. That is division algorithm. So you want x. X is equal to 5k plus 2 divided by 3, where x should be an integer. So you again assigning k value and see for what value of k I am going to get x as an integer. I will take k equal to 0. X is not an integer. X is equal to 2 by 3, which is not an integer. Take k equal to 1. We have x is equal to 7 by 3. It is not an integer. It is not an integer. Take k equal to 2. We have x is equal to 5 2s are 10 plus 2. That is 14 divided by 3. Again not integer. Take k equal to 3. We have x is equal to 5 3s are 15 plus 2. That is 17 by 3. Again not an integer. Again take k equal to 4. So 5 4s are 20 plus 2, 22. We have x is equal to 22 by 3. It is again not an integer. Again take k equal to 5. We have x equal to 5 5s are I should get 4 na, the value I should get 4, yeah, fine, we'll try. Take k equal to 5. When you take k equal to 5, no plus for me to write. It is 25, 5s are 25. This is where I am using. 5 5s are 25 plus 2, 27 by 3. Yes, I got 27 by 3, which divides, it is going to be the 9. There is a mismatching with the solution. I got x is equal to 4. I need to cross check here. 8 equal to 7 by 3. K equal to 2. I had a mistake here. Is equal to 4. So we don't want this value. That's what. You should be careful. When you take k equal to 2, 5 2s are 10 plus 2 divided by 3, 12 by 3, which is 4, which is an integer. I can take this value as my x naught. Once you got the x naught, come back and fit into this expression, run the t value 0 to 2, I'm going to get the same set of solution. What is actually x naught equal to 4, 4 plus 5t, see, 4 plus 5t, t equal to 0 to 2, take t equal to 0, 4, t equal to 1, 9, t equal to 2, 14. So same set of solutions. There are two approaches. One is by inspection, one by modeling using division algorithm. This is the case when you go with a linear congruent. Why linear congruent is very, very important? One very special case of linear congruent is finding the inverse under linear congruent. I would like to go with that now. One more approach is to find solution of linear congruent is GCD approach. I can show you one more case here. One more method. I can say the third method. What is the first method? Inspection. Second method is modeling. Third method is going to be using Euclidean algorithm. That is using Euclidean algorithm. I will take the same example. We have 9x is congruent to 6 mod 15. So we can write 3 times 3x is congruent to 3 times 2 times modular 3 times 5. I can get rid of the 3. 3x is congruent to 2 mod 5. Now you take the original expression, get the GCD. So I will find the GCD of 9, 6. I told you very clearly, always I will prefer to go with Euclidean algorithm. Yesterday I told you, last class I told you how exactly we can find the GCD, extended Euclidean algorithm, or expressing the given GCD as a linear combination. That's what we are going to do here. Take A, take here B, take A here, take Q, take R, and write R equal to B minus A into Q. Directly one column we can reduce. What is B value? Bigger. What is small value? R. 6. Now using simple approach, 6 ones are 6 and additional value is 3. This is quotient, this is remainder. Now we can write the remainder as 9 minus 1 into 6. I wrote the formula, just substitute there. Now you shift the A value, shift the R value. Again you find Q and R here. It is going to be 0. 3 2s are 6. No more R value is required to get 6. So we got. What is my GCD? The GCD is moment you get the remainder 0, the previous value of the remainder which is not equal to 0 will be GCD. This is my GCD. So we have the GCD of 9, 6, that is G equal to 3. And 3 divides 15, it has 3 solutions. Many solutions, and strictly speaking, 3 solutions are there. Incongruent solution. Now how to find that incongruent? Again the same, the previous method what we got here. we can write x is equal to x naught plus t divided by, or I can say here n divided by g times t, that is x is equal to x naught plus, what is n value? 15, and what is g value? 3. It is going to be 5t, where t running from 0 to 2. Again, the question is, I should find the x naught. X naught you can find using 3 methods. One is inspection method, modeling method, another is Euclidean, extended Euclidean algorithm method. I would like to go with extended Euclidean algorithm method. One problem, I am discussing 3 different cases. Whichever the method you want, you can follow. Now what I do here, I will apply extended Euclidean algorithm. Extended Euclidean algorithm, basically it is LC, linear combination. We can write 3 equal to 9 minus 1 into 6. So we can write that is 3 equal to 9 times, or I can say 9 times 1 plus 6 times minus 1. So we have 3 equal to, it is 9x plus 6y. And 9x plus 6y. And what is x value? 1. What is y value? Minus 1. But I know that no value of x and y should be negative. So immediately I can convert this as minus 1 plus 5, that is equal to 4. See, I got it now. What is your previous value? X naught equal to 4. What is your y value? 4. So your y value, that is x naught equal to 4. Now substitute 4 here and run the t value 0 to 2. I am going to get all the 3 values. Again there are 3 approaches. Again I am recalling because this is very important for next level. When you have a linear congruent, first recognize that it has a solution. Next level, if it has a solution, how many solutions? Unique solution, many solutions. If it is many solution, remember the modeling x is equal to x naught plus phi into t. You know how we got it? Using formula x naught plus n by g times t, where t running from 0 to 1 less of GCD. Now the question is how to find the x naught. To find the x naught, there are 3 approaches: by inspection, by modeling, another one is using extended Euclidean algorithm. So once you got the x naught, you see Euclidean algorithm, be careful, be cautious. Whenever you have x and y, see that x and y should be positive. X is 1 positive, y equal to minus 1, it is a negative. I should convert to positive by adding the divisor. What is the divisor actually? The divisor is phi. So y equal to modified. After simplification, the divisor is phi. So y equal to minus 1 plus phi. I don't want negative. Add phi is going to be your simplified version of the linear congruent, that is going to be 4. See, I got the 4, I got the 4, I got the 4. All 3 I am going to get generate the same value of x, that is going to be x naught. Take x is equal to x naught, substitute there and run the t value, I am going to get all congruent. My question is, this is not my ultimate work. My ultimate work is defining inverse of a linear congruent. Now we would like to go, that is very important. Once you understand that, Chinese remainder theorem is very friendly. Once you understand Chinese remainder theorem, your Diophantine equation become friendly. Once you understand Diophantine equation, your application of going till computer science application of cryptography is also going to be easy.